So we are provided a relation R which is defined from a set A containing the elements 2, 3, 4 and 5 to another set B having the elements 2, 4, 5 and 8. And the relation is such that the ordered pair x and y, x divides y. So let us try to form the relation. So we first pick up an element. So this is a relation going from A to B. So we start by picking up an element from set A, which is 2. So let's say we start with our element 2, which belongs to set A. Now we'll try to form a relation between this element 2 with each of the elements of set B. So we'll check 2R2 and we'll see if our value y is divisible by 2. Indeed, 2 is divisible by 2, so that means this indeed forms a relation. So it's going to belong to our relation. So this gives us the first ordered pair 2, 2. Then we move on to the second element in y, which is equals to 4. So 4 is divisible by 2, so that means this is indeed a valid relation. So this is also going to our relation R. So 2 and 4 is going to form the second ordered pair. Then we move on to 2R5. Now we see the 5 is not divisible by 2, so the relationship is not holding. So we'll say that this does not belong to our relation R. So this is not going to form any ordered pair. That is going to belong to our relation. Then the final element in set B, so we'll have 2R8. Now 8 is divisible by 2, so that means this belongs to our relation and this is going to form an ordered pair 2, 8. Now we pick up the second element from set A. 3 belongs to A. Now from here we see that none of the elements in set B are divisible by the number 3. So we'll simply say that 3R2 does not belong to the relation. 3R4 does not belong to the relation R. 3R5 also does not belong to a relation R. And finally 3R8 does not belong to the relation R. Then we move on to the third element in set A, which is 4. 4 belongs to A. This implies now if we look at set B, the only the values that are divisible by number 4 is 4 and 8. So we have 4R8 is 4R8, it belongs to R. 4R4 also belongs to R. So 4R8 belonging to R, this is going to give us one ordered pair which will be 4, 8. And 4R4 belonging to R is going to give us another ordered pair which is 4, 4. Then we move on to the fourth element in set A, which is 5. 5 belongs to set A, and we see that there is only one element in set B that is divisible by 5, and that will give us 5R5, and this belongs to our relation R. So we'll get the final ordered pair which is 5, 5. So therefore the relation R, which satisfies the conditions that x divides y, will be finally given by 2, 2, 2, 4, 2, 8. And we have 4, 4, 4, 8, and 5, 5. So there are going to be 6 ordered pairs which satisfies the condition that x divides y. So this is the roster form. So we can also write in the set builder form. So that will be R is a set containing the ordered pairs x and y such that x divides y, then x belongs to the set A and y belongs to set B. So now that we have this, will be the set builder method. Now that we have the relation in the roster form, what we can do, we can figure out the domain, range, codomain of the relation. So let us do that. So the domain, the definition of domain states that all the first element of the ordered pair in the given relation will be the domain of the relation. So we see that the first element in the relation are 2. So 2 is repeating, so we'll only count it once. So 2. Then we have 4. 4 is repeating twice, so we'll only consider once. And 5. So the domain of the relation will be 2, 4, and 5. Then the range will be all the second elements in the ordered pair. So that will be 2, 4, 8, and 5. So we have 2, 4, 8, and 5. And the codomain will be the entire set B. So our set B contains the elements 2, 4, 5, and 8. So clearly here we can see that our range is a subset of the codomain. Now we can also represent the given relation graphically. So to represent the relation graphically, so we draw two Venn diagrams. With this, the first Venn diagram will comprise of this elements from set A, and the second one will consist of the elements from set B. So starting from the first element in set A, which is 2, so 2 forms a relation with 2. So we draw an arrow going from element 2 to element 2 in set B. Then we should also we should also specify the arrow. So this is going from set A to set B. Then we have 2 also going to the element 4. So we'll draw another arrow going from the element 2 in set A to element 4 in set B. And then we have an arrow going from 2 to 8. Then 3, then the element 3 in set A does not form a relation with any of the elements of set B. So we move on to the third element, which is 4. So 4 is going to form a relation with 4. So we draw an arrow going from the element 4 in set A to element 4 in set B. And then we have also the relation between 4 and 8. So we'll draw an arrow going from element 4 to element 8. And finally 5. So the element 5 in set A is forming the relation with element 5 in set B. So we draw an arrow going from 5 to 5. So this is the graphical way of representing a given relation. So we have a relation going from A to B. So in this question we have a relation R that is defined on the set of integers, and the relation is given that the ordered pair x, y belongs to the relation R if and only if x squared plus y squared is equals to 25. So let us begin. So here we are given the set of ordered pairs x and y. This belongs to our relation R if and only if x squared plus y squared equals to 25. We can rewrite this equation in terms of y. So that should give us y is equals to plus or minus the square root of 25 minus x squared. Now we're going to consider different integer values of x. So let us consider x equals to 0, the first integer value. So that should give us y value as plus or minus the square root of 25 minus 0 squared is 0. So we have the square root of 25, the 25 being a perfect square, so that gives us y value as plus or minus 5. Now we can say that the ordered pair 0, positive 5 belongs to our relation, and the other pair, which will be 0, negative 5, this also belongs to the relation R. Now we consider x equals to 1. So for x equals to 1, we get y is equals to plus or minus the square root of 25 minus 1. So that gives us a square root of 24 plus or minus square root of 24. But 24 is not a perfect square. So that means this value is not going to be an integer. Since this does not belong to a set of integers, so this implies that the ordered pair 1 square root of 24 does not belong to a relation R. Now we consider the second value, x is equals to 2. We'll see that for x equals to 2 as well, the ordered pair is not going to belong to the relation because we'll get a square root of 21. So we'll move on to the third value. So let's take it as the plus or minus 3. So we'll get y is equals to the square root of 25 minus square of 3 is 9. So that gives us a square root of 16. 16 being a perfect square, we'll get plus or minus 4. And we know that 4 belongs to a set of integers. So that will give us 4 ordered pairs. The 4 ordered pairs, let me list them out. The 4 ordered pairs will be positive 3, positive 4. That will belong to R. We'll have positive 3 and negative 4 that belongs to a relation R. We'll have negative 3 and positive 4 belonging to the relation R, and negative 3, negative 4 belonging to the relation R. Then we move on to the fourth value for x equals to plus or minus 4. That gives us y is equals to plus or minus square root of 25 minus 16, and that gives us the square root of 9, which is equals to plus or minus of 3, and that being an integer. So we can form 4 more ordered pairs, and that will be positive 4, positive 3 belongs to R, positive 4, negative 3 belonging to R, negative 4, positive 3 belonging to R, and we have negative 4, negative 3 belonging to R. Then we take the next value for x equals to plus or minus 5. So that gives us y is equals to plus or minus 25 minus 5 squared, which is 25. So we get y equals to 0, that being integer. So we can form the ordered pair positive 5, 0, which belongs to R, and negative 5, 0 belonging to a relation R. Now for any other values of x greater than 5, we'll see that the square root, the value inside the square root will be a negative number, and that will take us to the complex domain. And since we have to stick to only integer values, so we'll not consider any values for x greater than 5, plus or minus 5. So let's list all the relations. So we have listed out all the ordered pairs for the given relation, and this is the roster form. Now let's find out the domain. So the domain represents all the elements, the first elements from the above set. So we have the elements 0, 3, negative 3, 4, negative 4, 5, and negative 5. These are all the first elements from the ordered pair taken from the relation R. So this will give us the domain. So likewise, we can also find out the range. So our range will be all the second elements picked up from the above ordered pairs. So here the range will be 0, 3, -3, 4, -4, 5 and -5.